Hi, in this week's lab, we're going to talk about planes, geologic planes, so surfaces, planar surfaces, and how we measure them and how we record them on paper. So I've just showing a picture from the internet of a typical rock outcrop. So these are sedimentary rocks. There's some pine trees for scale, some kind of dry creek bed. You can see that are the geologic layers here are tilted. This is pretty common. Sedimentary rocks they start out horizontal, roughly horizontal, and then due to different processes, geologic processes, they tend to get tilted. They get pushed up and or pushed down and folded. Interestingly, here you can see like a layer, the present day horizontal is kind of just some alluvium dirt sitting on top. But underneath these rocks are tilted. So we want to be able to um, sort of describe this in a consistent, efficient way when we encounter rocks. And so to do that, we're going to use something called the strike and the dip. Okay, so imagine a some dipping rock layer. And let's draw this in 3D. Imagine there's a sort of imaginary horizontal surface. This surface would cut through. Um, okay, so let's label this imaginary horizontal surface. Okay, so we're going to define um, two things. The strike, these two things will give us a complete description of any plane that's tilted. So the strike is the direction taken by a horizontal, actually by a structural surface for example, a fault plane or bedding. Bedding being the um, sedimentary, original sedimentary layering. As it intersects the horizontal. So that intersection, I'll use a different color here. Like the direction of this green line I'm drawing. So if we could, you know, take a compass and stand on this surface and see what direction that green line is pointing, that would be um, that would be what we call the strike. And the other thing that we need to know, so the strike would determine this direction, but um, we also have this angle, the angle that it's tilted at, which we call the dip. the dip is the maximum angle a surface makes with the horizontal. Measured downward. So this angle right there, that's the dip angle. And we will measure that different ways. We could, on this piece of paper or on this screen, you could measure that with a protractor. It's something like about a 30-degree angle. A little bit more space here. So the dip is always always measured perpendicular to strike. And in the vertical plane. So all that's saying is like there's a lot of different angles you could measure between this surface and that plane. If you could measure them at some odd angle, and you could get angles in there that are less than the dip. So we measure the dip perpendicular to strike. So you can see that here. So this is a 90-degree angle between the strike direction and the dip direction. So if we could mark, we'll just use a blue here. On the bedding plane, we could draw that's a 90-degree angle. And we should talk about the dip direction. So what is the dip direction? It's a direction the plane dips downward from the horizontal. And by direction, we mean compass direction. So on this diagram, we said it was 90 degrees. So like that direction I'm pointing there. So if the strike was north, the dip here is east. Let's call it that arrow, call it dip direction. Okay, so the dip has both an angle and also a direction. So it's dipping. This one is dipping. Let's say we had our compass here, and that's the direction north. So the strike is north here. The dip is east. So these names, strike and dip, might be familiar from faults. If you've heard of strike-slip faults, like the San Andreas fault. So this is a fault where the direction of motion is parallel to the strike. So here we have a vertical fault, and the motion, you can see this block on the right has moved sort of into the screen. So this is the slip on this is parallel to strike, so we call it a strike-slip fault. And there's another kind of fault called a dip-slip fault. So if this block had moved downward instead of sideways, we would call that a dip-slip fault. So here we have another diagram. This is basically the diagram we tried to draw earlier, just slightly different orientation. So the beds here are dipping to the west now instead of to the east as we drew it. And they're showing, so in green we have these dipping sedimentary beds, and the imaginary horizontal surface, you could imagine the water level rising. Sea level rises up, and water is always going to make a horizontal surface on the top. So you can, if you ever kind of forget what strike is, you might be able to sort of imagine water coming up and how it will make a line. There'll be a line between the rock and the water. And if we were to measure the direction of that line here, it's exactly north again. We call that the strike. So we could actually, in our class, there's different conventions, but we could also say the strike was south. And here we have again the direction of dip, which you can see is at a 90-degree angle. So if you were to slide down this slope, the steepest direction you could go would be at 90 degrees to the strike, and that's what we call the dip direction. So here the dip direction is exactly west, and it's dipping, and the dip angle is 30 degrees. So there's other ways you could go down the hill, at an angle like this. You would be walking down a 15-degree dip or some lesser dip. Later on, we'll talk about what's called a parent dip, which is if you measure at some other angle other than 90 to the strike, then you can get numbers that are less than 30 degrees. So we want to avoid doing that. I always use the true dip, 30 degrees here. So we have a symbol that we use on maps to record the strike and dip. So the strike and dip might vary from place to place. So we want to be able to, let's say we want to be able to walk around, let's say that this is north, and record what we find. So we're imagining we're looking at a map here. North is up. Let's say there's a river over here, and we find some rocks, and we find that they have a strike that's north and a dip that's east. So the way that we draw that is we draw a little north line for the strike and a tick mark on it to the east. And let's say that it was dipping 30 degrees, and we write a 30-degree, we write 30 there. So this indicates a north-south strike and a 30-degree east dip. We put that little tick mark off in the direction it's dipping. Alternatively, if it had been dipping to the west, 30 degree, this would be north-south strike, but a 30 west dip. This one here, okay? And let's say it was striking east, dipping south. See if you can guess what that's going to look like. That symbol would look like this. Let's say it was dipping 10 degrees south. Put a little 10 there. Okay? The lab has a couple other sort of unusual circumstances. There's a couple different symbols. We don't need to worry about those right now. So we could walk around in a map area and find, the rock, the strike and dip is either the same everywhere or it's changing, and we would record this in different places. There are sort of two conventions we use for the compass directions, okay? So for the strike. And these are given in the lab as well, so you can take a look at that. So here's a compass, north, south, east, and west. So we have an azimuth convention. And in this case, we call north 0. We go around clockwise. So this is 90, this is 180, 270, and you can imagine we go, anything in between. So in the azimuth convention, let's say we have a line like that. This would be something like a 40 degrees. A line like this would be, we could say either something like around 120. We could also use numbers larger. We could use the, instead of 40, we could have added 40 to 180 and said 220. I find it easier to stick to numbers less than 180. They're just easier to deal with. Okay, so this is one way we can describe a strike. We can use numbers from 0 to 360 using the azimuth convention. Alternatively, we can use the quadrant convention. So again, we have north, west, east, south. This is easy to remember. It spells we. Okay, so we have 0. So let's just label this quadrant. Okay, so in the quadrant convention, we always say, we say things like north 20 east or south 30 degrees west. Okay, so in this case, we start in a direction like north, usually north. It could be south. So we always write north first, and then we write a number. So 30 north, 30 east. So that means we start at north, and we go 30 degrees over here. So a line like that would be oriented north 30 east. North 60 east would be more like this. South 60 east would be, we start in the south, and then we go 60 degrees over somewhere like that, okay? So south, this would be a 60-degree angle. South 60 east, north 30 west. So we start in the north, we go over 30 degrees, something like that. So the same, if we were to, let's just look at these. So an azimuth, we can convert back and forth. So an azimuth of 40, the quadrant convention is north for 40 east. 120 would be, basically that's 60 degrees up here from south 60 east. I find the quadrant convention to be a little bit more intuitive. But the compasses we have both of these. We have some of each, and it's important to know how to use both of these conventions. So the quadrant compass is labeled with zeros and 90s. So in 45s or other numbers in the middle. So you always start at either north or south and go up to 90. Quadrant, the number in the strike for a quadrant will never be greater than 90. So we have a little movie here where you can take a board that's in water. It's got a strike and dip symbol on it, and you can rotate it around at different angles. So here it's steep, the beginning it's shallow, and north is up, and we can just sort of practice these concepts about strike and dip that we've just learned, and these are very important. We're going to be looking at strikes and dips throughout the course. So it's really worth your time. It's the basic observation, one of the most basic observations that geologists make. And it's a key part of the class. So it's worth your time early on to wrap your mind around strike and dip. So let's say that we have, here's our board. The line, where the water intersects the board, so the horizontal intersects the tilted board is north and south, right? So this would be a north strike and an east dip. With a quadrant convention, we would say sort of north 0 east for the strike. For the azimuth, we would just say 0 is the strike. All right, let's say, I think they go at, those are 30-degree increments. Okay, so here is a north 30 east strike. That would be the azimuth, the quadrant convention, or it would just be 30 for the azimuth convention. And it's dipping here, it's dipping to the southeast. Here we are at north 60 west strike, dipping southwest. Here is a strike of 0, dipping west. This is a east-west strike, dipping south. We can talk about, so things that are, when the board's really steep, we call that a steep dip. So that the dip is high, is a large number, so the angle here is probably something like 70 degrees. We would call that a steep dip versus one of these here. We call this a shallow dip. So this would be north 60 east strike, dipping shallowly to the northwest. And we want to become very comfortable with sort of qualitative descriptions like that, as well as more, being able to quantitatively measure these things and using a compass, for example. So let's come over to here. Okay, so this is about a north 60 east strike, steep southwest dip. This would be a north 60 west strike and a southwest dip. So I would, you could go back in this video and see if you can, I went through it for pretty fast, but you can, see if you can come up with the strike and dip descriptions yourself before I hit pause, before I say what they are. So this again would be a north or south strike and a steep west dip. So just a little bit more about map symbols for strike and dip. We always measure the strike with a protractor, okay? So when you draw the symbol on your map, that direction, you're recording the exact direction, and it might not be recorded anywhere else. So it's very important that you make use of the side of the paper or other lines there to actually accurately measure the angle of the dip. Each time you do it. So that means sometimes you can get a map and you can use a protractor to collect, in a table form, all that data. But we also always write a number, the dip number here. So this symbol has all of the information about the strike and dip. It has a dip, or it has a strike. So here it's something like north 60 west, something like that, and it's dipping 30 degrees to the southwest. So this would be, let's write that down. This would be a sort of north 60 west. And we would write 30, and we would just write south. So actually, even though this is dipping south and also a little bit west, all we need to do is write the S, because really the question is, okay, we've drawn a strike north 60 west. There's only two possible. Let's say we know that it's dipping 30. There's only two possibilities. It's either dipping 30 to the north or 30 to the south. So putting the tick on the south side indicates, yeah, it's the southern choice. So we don't need to write southwest here. So we just kind of save space by just using one letter. So sometimes if it's dipping like, or if it's striking here like north 45, this would be north 45 west. In this case, it really is dipping both west and south. So let's say this was a 40, the angle of the dip is 40 degrees. We could write, it'd be fine to write southwest here, or 40 south would be fine, or 40 west would be fine. These all indicate the same thing. They indicate it's not that. That would be northeast. So it's very important. So make sure you're very clear about what that 40 degrees means. So the 40 degrees is not a compass direction. Okay, 40 degrees is, if we were to draw, those rock layers tilted, it's the angle that they're tilted down. It's the steepness of the slope of the rocks. So if you were gonna roll a ball down the slope, acceleration is going to be determined by this angle, 40 degrees. So it doesn't have anything to do with the compass direction. So the strike is the part that has the north and the west. Well, for azimuth convention, we would write this north 45 west would actually be sort of 360 minus 45, whatever that is. You can see why I don't like azimuth as much. In quadrant convention, we have north 45 west. This is a compass direction. It's a direction we could walk in. And then the 40, even though we put a compass direction on it, southwest, the 40 itself is just this angle. And the reason we can't represent that angle looking down on a map from the sky, we can't really tell the tilt very well. That's why we have to write the 40. We can't measure. There's nothing we could measure on here. So a couple other notes. The tick mark for the dip is always drawn 90 degrees to strike. Okay, so that angle between the tick and the strike is always 90. I never want to see a mark like that. Okay, that doesn't, there's no such thing. Okay, bad. We try to actually draw, I'm not doing a great example here, but we try to draw these nice and neat using a straight edge. So I can do that. You'd put your protractor there and you draw a nice straight line. Because, like I said earlier, we want to actually be able to use, when you look at the map, we want to be able to, there's meaning in here, and if you've got it at different angles, it's confusing. It's hard to be sure what actual strike this was. This is close enough to 90. It's hard, you don't have to use your protractor to make that exactly 90-degree angle. Yeah, so wait, so this was the 40 degrees. So there's like, this would be like the surface is the pine tree, rocks dipping at 40-degree angle. So most of this, or some of this information is also covered in the lab. And I think you've gotten, at this point, pretty much most of the information you need to do the lab. The last part of the lab asks you about some impossible situations. For example, if the strike here's a northwest strike, right? This one. Northwest strike. The dip has to be either, I said, northeast or southwest, right? It's going to be a tick mark on one side or the other. You couldn't have a northwest strike and a northwest dip, or a northwest strike and a southeast dip, because that's the direction of the dip is defined to be 90 degrees to the strike. So those questions deal with that. So, and that's a way to kind of check your when you're recording a strike and dip, you can sometimes find an error because you've written something that's like not actually possible.